Hello and welcome to Advent of Code in F#, day 24. We're this close to the finish line, I can almost smell it. So let's see what today's puzzle has in store for us. This is not today. That's better. Go crab. We make it to the tropical island. Oh no, tile floors and hexagonal tile floors. Interesting. Hex grid with a very specific color pattern. Are we going to do K coloring? Graph coloring? Cool. No, it's only two colors. Start with the white side facing up. Lobby is large enough to fit whatever. Total input is the list of tiles that needs to be flipped over. Each line references a tile, and they all start from a reference tile. These tiles are hexagonal. Every tile has 6 neighbors. That's what a hexagonal means, yep. Okay, so the hexagons are pointed with the pointy sides on top and on the bottom, yep. Let's maybe draw a hexagon just as a reminder of what grid layout or what tile layout we're working with. So we're working with hexagons like this. And I have an east and a west. Oh, this is the worst hexagon in my life. So hexagon. Northwest. Yeah, okay. Tiles identified by directions with no delimiters. SNE. East, southeast, northeast, east. Yeah, okay. Flips from white to black or from black to black. So each time we identify a tile, it flips. Yes. Might be flipped more than once. Cool. A line like east, southeast, west. East, southeast, west. Yeah. Okay, it all makes sense. This is a larger example. Cool. Total of 10 tiles of black. This seems really doable, actually. The only thing I'm not sure of is how will we, what coordinate system, how do we identify locations in a hexagonal grid or a hexagonal board? There has to be an easy an easy way to work with these things. Hexagonal grid coordinates, there we go. Rejects the square lattice. Academics. So just use 3-dimensional. All points are equidistant at 1 unit. Yes, this sounds interesting. Let's use this. How does it work? We have an x-axis going southeast, the y-axis going northeast, and the z-axis going north, but there's never a Yeah, let's use this. I'm going to need this next to me. So we start at origin. That always works well. So 0, 0, 0, and then we just, it's a bit like the game of life thing. It's an infinite space. We move around and we start flipping bits. Cool. Okay, let's start. Do we have input? We probably have input. Oh. Okay. We have a lot of input. There we go. So can we read our input? And we're good to go. Let's maybe first parse the input into something we can work with. Let's make a union type. So dear northeast, east, southeast, southwest, west, northwest. That's 6, right? 1, 2, 3, 4, 5, 6. Yes. How do we parse the input? Because we let's just munch the input strings 2 characters at a time, or with a look ahead of 1. Yeah, that will work. So let's parse a line. Let's call it parse path. Let's just do this with pattern matching. So the string is empty. We don't have anything to say. Maybe match on path instead. There we go. If there's only one element, same. And otherwise, let's look at 2 elements at a time. Let's make this recursive, or should we use Taylor version? Doesn't matter, it's not that much input and we only have to parse it 1. So A, B, and E, so we have northeast, and we parse recursively into, so we eat, or we munch the B so we don't have to look at it again. Oh yeah, so this is a, it can be east. Then we go east. It can also be west. Yes. Sure. Pattern matching works well for the structuring. Works a bit more cumbersome when we're doing guard clauses like this, but okay. So we can parse west and east. We can parse northeast. Southeast, southwest, northwest. So southeast, northwest, come on, so that's northwest, and that should be southwest. Cool. Let's try that on a random input string. It's saying incomplete matches. Yes, yeah, we're matching our characters. Doesn't matter. Let's take an example. Sure. Let's do the cumbersome conversion hidden away from consumers of this function. So this takes a string, and we just go Yeah, there we go. Match failure expression. Interesting. What? Did not expect this. I did not call this. What case is this not seeing? So if we see northeast. Oh yeah, we can still see east and west further below. Like not as the final character. So if it's east, and now that I'm typing this, I see that I could have written the previous things shorter, but okay. So this is east, and we need to do the same for west. So this is the east case, and this is the west case. And this means actually when I do this guard class, I can just do it inline here. Thanks, pattern matching. And then we can get rid of this whole when and constructing a tiny list just to do the guard. That's better. Yeah, that's better. Northwest. And southeast. That's not correct even. South. So guards can go. Then there's a bit more symmetry in our code. Whenever there's whenever I lose symmetry, that's a potential smell. So nothing, we're done. Single character, we don't even need to have these cases then actually. So this was actually good enough. Northeast, southeast, northwest, southwest, east, west. Yes, Yoko. That looks correct. It's not tail recursive, but as I said, we only have to munch this input once. It's not really going to be our performance problem of the day. Does this look correct? Southeast, southwest, and we end with the southwest, and there's some east in there. Is there some west in there? Yeah. Let's give this the seal of approval. There we go, seal of approval. We're done. So now we have our input parsed, or at least the hard part is done. We have our coordinate system thought out. Now just let's just loop over all the lines and start flipping tiles. So whenever we loop over stuff and have to thread state through it, fold is my go-to function. For fold you need state. Let's make that very explicit by encoding it in a type called state. And so this keeps track of, actually this is just a lookup table of a coordinate. Yeah, it won't change today. It'll be 3-dimensional or hexagonal, sorry. So we can represent it with our 3-dimensional grid. So it takes 3-dimensional coordinates or an XYZ coordinate as a key, and the value is state, which is white or black, right? White and black, yeah. So let's encode that as well in a color, white or black. There we go. And maybe case it correctly. So it's a map of position to color. That's not how you... Can I do this? Probably I can. Don't know how. So I don't have to use the generic type braces. That reads. I've been using this syntax for the whole year, the whole month. But when you do, for example, if you have an option, you can type it as a option string. Yeah, so this type checks. This is valid syntax for a type definition, but you can also say string option, and that's actually the same. And I'm wondering if you can do this for the map type as well. What would that look like? So probably it would be this something map. How do you do multiple type arguments? We're digressing. Maybe map with a big M. No, it's not happening. Never mind. I'll figure that out on my own time. So we have state, which is just a lookup table. Does everything start with a default color? Probably. Yes, everything is white. So let's keep that as a default color. And because our grid can grow infinitely large, if we don't have it in the lookup table, it's by default white. So it's exactly the same as GameApply or the multi-dimensional hypercube thing from this view. Yeah, now we just have to figure out how we take a step, and that's using this coordinate system. So let's grab that next to us, and let's maybe keep a reference to what we're using. There we go. So given a location and a direction, we need to be able to move. So let's try that. Given a location and a direction, and location is X, Y, Z. Yeah, let's go. Let's maybe get rid of this. There we go. And no, that's good enough. We're using an option type, so we can exhaustively pattern match. Cool. Let's do. Let's calculate the relative, the vector where we have to move. So if we are going east, it is 1, 1, 0. Literally, what the picture is saying. If we're going southeast, 1, 0, -1. Let me just hammer this out. It's having a new keyboard and having to type all these weird things that are not English. It's it's not a habit I learned quickly. 1, 2, 3, 4, 5. What are we missing? Northeast. 0, 1, 1. So we can go this, and then we can just do. Let's make this offset. Let's destructure it directly there. So the new coordinates, if we take a step down, direction is. There we go. Let's proofread. East, yes. Southeast, yes. Southwest, yes. West, yes. Northwest, yeah. Northeast, yeah. Okay, that looks correct. So now we can move. We have our state. I think we're there. Everything starts at white. Yeah, okay, cool. How do we name the thing we're doing? Let's just call it flip tiles. Flip tiles given a state and a current path. Okay, we can take one step, but actually we don't need to take one step, we need to follow the entire path before we have to do something actually. So let's do that first. So let's do let follow given a start and a path. If the path is empty, we're done. We're at the location. Otherwise, direction and the rest of the directions we can move or start in the direction and we follow recursively. We don't need to keep track of the intermediate states just yet. That might be part 2 stuff. And follow the remainder. So this is following an entire path. I think now we're ready for the fold. So flip tile given a state and a path is we always start from the same relative position, right? Oh, come on. Oh, come on. Every line starts from the same reference. So yeah, we can start to flip given a path from origin. So follow the path starting from origin, and let's flip at location. So we need to flip. State is our lookup table, so this knows about our lookup table. It has to go below the type declaration. Flip state at location. Maybe do the arguments the other way around, so it's something like state flip location. That reads a bit better. So we try to look up state, and no, we don't even have to look up state. Just dump it in there. So state. We do have to. We're flipping. We're not overriding. Sorry. So if we have nothing, we just so it means it's white, we have to make it black. If it's some color, some white, we make it black, otherwise we make it white. So nothing means white. White means white as well, so these two are actually the same. Come on, I know you can, yeah. And black is just making the tile white. Why? Follow. I got my arguments mixed up. So this is flipping a single tile, so input these are our instructions or our paths, and then we just fold over using our flip tile, and the initial is an empty map. I think this is about all we have to do for part 1. Let. Okay, let's load everything in the Ripple. What? I'm sorry. Yep, we did some flipping. What do we have to do actually? How many tiles are left black? So, let's just rename this and let's get the blacks out. Let's rip it out. Let's rip it out. Let's throw away the locations, and let's keep the blacks. And let's count them. That's a smallish number. Is it too small? That is too small. Okay, let's go to the example. Okay, so this should result in 10 tiles that are black. Let's grab the Solution Explorer. This is anything but the Solution Explorer. Control Alt L. Let's quickly make a example.txt. Plonk. Okay, let's work on the example instead. Where's the problem? Is it in our flipping or is it in our parsing? 15, so yeah, that is not correct. Or are we going to have to draw this out? Or let's maybe... Is it 1, 2, 3, 4, 5, 6? What is it, 20 lines? Should be 20 lines of input, right? Yeah. I'm thinking, we have 20 lines. We are supposed to get 10. It seems like our coloring might be off. Oh dear. Our coloring was off. So, if it's white, it turns black. If it's black, it turns white. That makes way more sense. What are you giving me now? Yes, much better. Let's do this on our input. Ah! Is this not exactly the same? Okay, let's try it, but still, my gut feeling is saying too low. No, It's okay. Forget I said anything. This was a fun puzzle. I never used hexagonal coordinates before, so learned something new today. But now, well, actually, it's a small days. What? This needs coffee. Oh, that would be really cool if lobby floors were living art exhibits. Every day the tiles are flipped according to the following rules. Now we're playing Hexagonal Game of Life. I love it. So yeah, this is Game of Life again. Cool, so we have to calculate neighbors again. We've been through this before. Yes, exactly the same. I would have loved it if this was not the case. If like they didn't apply simultaneously or something. Because now it's literally Game of Life for what, the 3rd time this year? Wait a second. So we take what we got from part 1. But yeah, otherwise everything is white. And everything is not related to a puzzle. We take what we got from part 1 probably, and then we tick for some days. And we just need to tick 100 days. This is very doable again. After we build our initial world or initial map, we just tick for 100 cycles, applying Game of Lifestyle rules with the small twist that it's a hex grid, but it's 3-dimensional. We've already done this. I got this. I got this. I am actually a bit happy that the puzzles are teetering down a bit, because day 20 was brutal. Okay, but let's continue on. So this is our initial floor. Yep. We don't need, what do we need? How many tiles would be black? We need that as well, so let's call this so let's keep this function around, and let's call this initial. So state, rip it out and just formatting a bit so it makes sense to us an hour from now. Okay, this is the initial coloring, and now we have to do the math, or do the Game of Life math. We need to apply the rules, we need to fold over it 100 times, or we need to recurse 100 times. So we need, again, the neighboring coordinates, which are actually all these are all the neighbors, right? Yeah, these are all the neighbors. So let's grab this, and let's build a neighbors function that returns all the neighbors given the location. Let's keep part 2 stuff maybe at the bottom. So this was all, yeah, let's put it here. This is our solution code, so let's take that out. Let's put that in the bottom. Okay. This is now the 30,001th and the first time I write Game of Life. Never gets old. Yeah, it does get old. I wanted to say there's not much of a challenge after this many times, but I am bound to introduce a bug the second I say that. So let's keep our minds at it. So these are the 3, no, not the 3. These are all the offsets in the 6 cardinal directions, or the 6 directions. And let's just return them all applied to the location. Let's destructure as well. There we go. So these are the neighbors. If we can get 6 neighbors, we can count how many of a certain color we have, and that was something we needed, right? I'm not just doing this out of habit. Yeah. KKK. Yeah, let's write our tick function, or we start at day 115. This can be enough by 1 kind of thing. So our initial thing is day 1. Let's remember that. So let's write a next day function. Given a state, returns a state, but it has to do something. Do we need to clean house? Do we need to keep our map small? Maybe if things start to burn up, but otherwise let's not worry. So we grab every tile in the universe. Sure. CPU cycles are free today. So these are actually all the tiles. And we need to do something for all the tiles. What do we need to do? What do we need to do? Actually, it's a bit more interesting because, so for example, in our lookup table we have tiles, but those are not the only tiles we need to look at. We also need to look at potentially neighboring tiles, because tiles can come alive. Yeah, so if a white tile, so this in our implementation, this potentially means it's not in our map. And if that has exactly 2 black tiles, that could be the case. So we have to look at everything we know about and the neighbors of everything we know about. So it's actually state. And for every coordinate in there, let's find the neighbors. So and state itself as well. So we're saying every interesting hex is this state and the neighbors of every state. And don't do double work, so these are all the interesting grids, or interesting hexes. Yeah, it's a bit of overkill, but it works. And then for every hex, we just take a look at it, apply the rules, and go. And if we never update state, if we keep everything immutable, it'll work. So hexes. Are we making a new lookup table? Yes, we're actually always making new lookup tables, but it's not a problem. So we need to end up with a final aggregated result. Let's call this apply rules. Yes, let's call this apply rules. And let's fill in or feed in the state. So this function takes state and a hex. And hex is a one of those tuple things. So it's a value in the map, or at least that's what I'm trying to do, and it returns state. Yes, so these are tuples. We don't need the color to calculate neighbors, we only need the locations. Come again? Let's give this it's an explicit type. I'm not sure what's happening. Oh yeah, state is a lookup table, and that's interesting for this part. It's not as interesting for this. Oh, come on. Not sure what's happening. Okay, let's do that over here. Actually, it's not the first time that this stumps me. What's happening? So this is a list of coordinates and colors. So if I map over it, and I expect to do like grab the first and after that calculate the colors, that's not really working all that well. Why is this composition thing not lining up? Oh, it's saying seek, seek, seek. Ah, there we go. Oh, come on. What does neighbors do again? Yeah, just the location. Okay, I'm trailing off. I'll figure out what I'm doing wrong later. But it actually doesn't make sense. Okay. If this doesn't work, then we have an actual problem. Expecting A. Hexes should be a list of three-dimensional things, right? So type inference is magical until you do something wrong, and then it gets really tricky. So grid is, yeah, and then we say grab the coordinates, yeah, and then we say where we coordinates, grab the neighbors. Oh yeah, that's a list of lists. Yeah. That's why the types were not lining up. Yeah, we need to do that here. Oh no, so we map every grid to a single location, and then we map that single location to a list of neighbors, and we flatten that list with a collect. Yeah, what's wrong? Why does it want? Let's keep this. Let's keep this out of there. Is it just my code? Yeah, okay, it was just no. What's happening? Int. Oh. No. Yeah. No, that's a tuple. Takes tuple, returns a list of tuples. Let's write out the lambda. It should not give me any more information, but why is it expecting a? Why is it expecting color? Why are you expecting a color? It makes no sense. Yeah, so this knows nothing about colors. That's correct. Why is this confusing? This is grid. Oh, and if I say map first, it should return the list of coordinates, right? For every coordinate, do this. What's wrong? Yeah, this should be correct. Where are the colors coming from? Oh, it's this. Yeah. Whew, this took me way too long to figure out. So we're list appending the original coordinates, but they were not coordinates. They were coordinates and colors. Oh dear, this took a while. But no harm, no harm. We're not here for the speed record. So take our initial grid, take all the neighbors of the initial grid, throw away duplicates because we sure will have duplicates, and then we can move on. Okay. For every hexagonal space, apply the rules given the current state and feed that the initial state. What? What's happening now? What's it saying? So apply rules takes something and something. It's saying wait, let's type this explicitly again. Why am I getting confused in types today? Oh dear, this is the problem. Trying to do too much. So yeah, this is better. So we say for every hex, apply the rules and keep your result in a state. And the state is actually our state, so this returns. Okay, so now we reduce the problem to applying the rules. We need to find the number of black neighbors and the number of... No, we only need to find the number of black neighbors. So okay, what was it? A location and a state. Oh no, we need to look up, sorry. So these are all the neighbor locations. Let's look these up. And if they are not there, they are white. Let's make that more explicit. So now we have a list of maybe colors. So we can do a option dot no list dot choose, and because Eric chose the colors, or we chose our default value to be white. If it's not in the map, it's map.tryfind returns none. So choose throws away the whites that we don't know about. So these are the sums. And we just need to count them, which are all the blacks, yeah. There we go. So these are the number of black neighbors. There we go. Now we can actually this, the look it up and mapping it to, we're going to need to do that for hex as well. Why are we throwing away? Why are we throwing away? Oh yeah, because we're outside of the known universe sometimes. So yeah, let's just do the lookup here. So let's get the hex itself. State, same thing. Map, try find, location, and if we don't find anything, it's white. If I can spell white at least. So yeah, so we look up this current hex, and if we don't find anything, it's white. This we could actually encapsulate in a function and then use it here as well. Yeah, that's a bit more clear than this weird choose ID thing. So let's do a tile color at given a state and a location, and it's literally this part. So it's saying state, try to find it. If it's not there, return white, and otherwise return whatever is in the grid. So it's actually state lookup. What was it called? Color at. Why is my mouse a pointy finger? Never mind. So we can actually do the same thing here. So it's a map. It's a color at thing. Color at state. So yeah, let's get rid of this. There we go. And now we're getting our arguments mixed up. There we go. Makes sense if you have these multiple arguments. It makes sense to keep the argument that changes less frequently. For example, if you're writing a nested loop, write the variable that changes most frequently at the end, and then you can do partial application like here. You can provide a state and you don't have to write fun lambda syntax. But it's all details. That's not where the real money is in software. Hex color. Yeah, now we can just write our rules. That's a bit more clear. So there we go. We can just write the rules in a single pattern match now. Let's get the rules next to us. Any black tile with 0 or more than 2 . So if it's black. White, Kentis. Okay. Let's stay next to each other now. So any black tile with 0 is flipped to white. Any black tile with more than 2, so n larger than 2, also white. Any white tile with exactly 2 black neighbors is flipped to black. So I think this is it. black with 0 or more than 2 immediately. So it's split white, yeah, and exactly 2 black tiles, a white with black. So this is the color. And if we just have this return the location and the next color, I think we can use this. What's the problem? Yes, we don't need to do this anymore. So take the neighbors, get the colors, and then we do need to filter. Whew, glad I catch this again. But it makes more sense reading it this way than with the option magic. So this is a nifty trick to grab out or to filter out things in a list when you have a union type. Just saying pattern match. If it's black, yes, we want to keep it. Otherwise, let's not keep it. This is not exhaustive. This is not exhaustive. What do we do? I think we do nothing. So in every other case, let's just keep the color. There we go. Next day, yes, yes, yes. What's not to like? Let's line up some types. So apply rules, and this is a int, and it returns a new state. Ah, yeah, it should return a new state. Right. No, yeah, no. It should return. Oh yeah, let's just update the state. So let's do a state. There we go. So what does this now return? It takes a state, it returns a state. So it's a pure fold signature. And that is actually how we are using it. So that makes sense. So this takes one more day. And now we just need to do more than one day. So if we are done, then stop doing things otherwise. Do the next day, given the state, and recurse. Yep, should work. We've been flying completely blind, just typing out pattern matches. 0 tests required. Let's try this on the example. So we can build our initial board. That was part 1. And for part 2, we need to look at 100 days. I think if we do this, the off by 1 thing works out. Let's see. Let's take days 100 given initial state. And let's count. Come on, we had this function to number of black tiles. Let's do that. Let's rename that quickly to count. Are you a warning or no? You're a warning. Are you seriously? I did not expect this to be computationally expensive. So or we have an infinite loop, or we might need to clean up our data structure with like obsolete data. Actually, what are the rules again? Is this something that grows really quickly given white? No, you need black tiles to start having rules trigger. So if we just remove white tiles from our map, that will not hurt. Let's print out the number of days. What's going wrong? So what's going wrong? Okay, we built our initial map. Let's go. Yeah, it is actually coming to a grinding halt. So let's clean up our state after every day. Like throw away white tiles because those are implicitly white. Or everything is implicitly white. Is this the correct number at least? Definitely not. Oh. Let's print out the number of black tiles as well. And let's do I'm off by 1. I surely must be off by 1, but that's not okay. That's not a problem. Let's keep those in a single print statement so we can see what's happening a bit more clearly. So we print out whatever. Whatever. I think this will give us a bit more insight into what's going on. Okay, there we go. What are you doing? Stop. Stop right now. Let it tick, then I can enjoy my morning coffee. So it appears we have a problem. Let's diff our outputs. It's not supposed to be 10, right? That was the problem we had initially. So actually our first thing is going wrong. How can we have regression in part 1? Are we using the example? Yes, we are. The example is pretty small. Yes, that is correct. What changed to our part 1? What? Confused. I am so confused. How can our initial thing start breaking all of a sudden? Yeah, this was a bug we had, but it's very much fixed now. White turns into black, black turns into white. Cool. Counting black tiles. Is this happening correctly? Get everything. Keep colors. Keep black hexes. Count them. Neighbors, color add. We don't use that. What do we use to build the initial state? Only the flip tile. So our bug has to be in parse path or flip tile. Follow path. We didn't change anything, did we? No? How? Am I dreaming? 5 to 8. Let's see if that still works. Did we get lucky with part 1? Oh dear, we got super lucky for some reason. Huh? So it works for our huge. It works for a huge input, and it fails for the small example. Yes. Well, that is a shame. Oh no, it doesn't. What am I saying? I was confused by the 1015. It's super correct. So I'm sorry. So after. So it's not off by one thing. Oh, damn. So it starts. We start with 10, but after 1 day it turns into 15. Is this what we're seeing in our output? Okay, you can stop now. So it starts at 10 and it should take to 15. No, it's not. 10, 10, 70, 22. That's not. No, we have a bug. Oh. Sorry. Yeah, I'm going to have to draw this out. I think I'm going to draw out the hex grid on day 1 and then apply the rules of this small-ish example on day 2. And hopefully trace the problem. Let's maybe quickly do a cursory read of the code and hope that the problem pops in our eyes. So building the initial state, that works. We can assume that works. So the problem is right here. Days. Days does something wrong. Days is just recursing for a given amount of days, yeah. And we're counting down and we are calculating the next day. Yeah, next day. Given a state. Grab all the known coordinates. You know what? I'm gonna throw away the white. That will help with troubleshooting as well. So throw away white tiles from our input. I think that also speeds up the process of ticking days significantly. Yeah, it's not super fast. It's not really helping very much. I thought this would make it fly, but no. Did this just change? Did my removing of the tiles just change the outcome? I thought this would just be a performance tweak. So we have 7,969. Okay, so it's a bit faster. We are at 11,000. How can a so-called performance improvement how can that affect functionality? So this might be a hint to where the problem is. Yeah. So throwing away white tiles affects no, the only thing we do need is black tiles. I don't get why. Où est le work? I'm going to take a little break. We've been hammering at this problem for an hour now. We're really close. I can taste it, but there's a bug somewhere. So I'm going to start writing some test cases, debugging this neighbors thing because I have a gut feeling it might be there or maybe here. I don't know what's going wrong. But I'll see you at the other side of the tunnel. Well, that was fun. Or actually, no, not really. I spent the better part of an hour, I spent the better part of an hour troubleshooting, and I found my bug, and it's a face palmer. So what did I do? There we go. I took the example. I path weight every single path. I made sure I had the correct locations, and then I made sure that the rules applied correctly, and I had a problem in applying the rules. And the problem I had was super stupid. Can I hit diff? I can probably hit diff. The problem was really stupid. Where is the problem? The essence of the problem was here. So I was like boasting about how I finished the Game of Life 30 times already and how immutable data structures are amazing, and I go and apply rules and I don't keep the original state. If you use a fold to apply every single rule for following cells, you are not keeping the original state. So this was actually a very expensive mistake for me, because I spent an hour drawing hexagonal grids. It was interesting, it was fun. I even had my partner dictate the paths because I was getting confused. So it was a fun activity for half an hour, but it was totally useless because I made a mistake in my algorithm. I folded instead of doing changes in lockstep. So I also did some minor tweaks. I initially used the map, I think, and now I use a set because halfway through refactoring and troubleshooting, I figured out that actually we don't need to keep track of the white hexagons at all. So if our state just contains the coordinates that are black, that's enough. So I refactored stuff a bit. I put everything set related or state related away after behind these functions to have some kind of abstract data type. So the rest of the code was not really impacted by my refactoring. But yeah, so if we make something black, we add it to the set of the location. If we make a location white, we take it out of the set if it's in there. And to count the number of black tiles, that's just counting how many locations we have in the current set. So nothing changed with following and flipping, or nothing too big changed. Neighbor calculation, there was nothing wrong with it was correct. So this was my problem. I was applying the state one after the other, so I just refactor a bit. So this just returns the next color for a given location, but the rules remain the same. And then so this is the main loop to calculate a day, and instead of a fold I now use a map, which is more correct. And after I have calculated all the updates to be, then I apply these updates to the state with a fold. So this was a fun part of today's puzzle. But all in all, I really enjoyed day 24. I learned that I should not be boasting about how expert I am in implementing Game of Life, and I hope to see you again tomorrow for the final puzzle in Advent of Code in F#. Bye.